Hello everyone. Let's begin our discussion on mechanism design. So this is the other part of the course where we are going to discuss the inverse of game theory. Now I hope that all of you have heard about the story of one king and two women who claims to be the mother of one child, and they bring the child to the king's court to decide on who is the real mother of this child. And the king has to decide on give a verdict on who is the real mother, and the king does not know and does not have any information about who the real mother is. Different versions of this story is available in different parts of India and elsewhere. The king decides to cut the baby into two and give each of these women one of these pieces. Now, listening to this, one of the women backs off and says that I give up the claim for this baby. And then the king comes to know that this is the real mother and gives the baby to her. As a whole, you can think of this as a brilliant idea, brilliant mechanism, which finds out, even without knowing who the real mother is, finds out who indeed was the mother. But if you think about this closely, you will see that there is a problem with this mechanism. So the problem is, if you want to implement this once more, now that you know the story, if another incident like this happens, what will both these women do? What if both these women give up their claim to the baby? Then the mechanism will fail. The king will not be able to find out who is the real mother. And that is what is known as the mechanism. This particular mechanism is not actually committing to its principles. So first the decision was to divide the baby into two, and then the mechanism designer, the king in this case, actually retracted and decided to do something else. So that is not the kind of mechanism we'll be discussing in this course, because we need some sort of a commitment of committing to the policy that has been designed at the very beginning. So alternatively, think about the following. So if the king asked each of these mothers to bid a value, so how much amount of money or wealth they are willing to pay to get this baby, and the policy is that whoever bids the highest, she will get that baby, and she'll have to pay the losing bid, the other person's bid. Now, presumably, who is the real mother must have a very high value for her child, and she will definitely win the baby, and the other person may have a very low value for this, and therefore she will have to pay very little. So this mechanism, and we'll discuss this mechanism later in greater detail, actually does what it commits to. So every time you run this mechanism, it is going to work. And that is what we are going to call as mechanism in this course. And the idea here is that we have a certain desired objective that is set in the very beginning. And the task for this mechanism designer is to set the rules of this game such that in those reasonable outcomes of that game. So in our context of game, we have defined different kinds of equilibrium, which we call the reasonable outcome of that game. So in those equilibrium, the objectives or the desired outcomes show up. So that will be our objective here. The examples of this situation are many. So election is one where every individual has some sort of a preference over the candidates who are contesting in the election. And finally, the objective is to select the topmost candidate, one candidate, or maybe multiple candidates. Or if you are trying to share a scarce resource like the spectrum or the cloud resources, and you want to give out to those people who really value it the most. So you want to design a protocol where the allocation will be such that it goes to the most valuable players. Or it could be matching students to universities. There the objectives might be different. We want to ensure that the students and the universities matching is kind of stable, and different other kind of properties are also satisfied. So these are the objectives of mechanism design, and now we'll have to design the game such that those objectives are met. So let us first discuss about the general model of mechanism design. As before, we have a set of players which will denote by n, and by x will denote the set of outcomes. For instance, in the voting example or the elections, the winner of an election is one of the outcomes. Or in the resource allocation example, which resource should be allocated to whom? That is one decision that the mechanism designer has to make. So all those things, all the possible such outcomes are put inside this set, capital X. Now, every individual in this context, in the mechanism design context, has some amount of private information. We have seen this kind of a setup even for the Bayesian game. So with capital theta I, we are going to denote the set of private information of agent I, and we'll call this private information set as their type. So a specific type for player I will be denoted by this lowercase of theta I, which lives in this larger set, capital theta I. Now the type, the way it manifests the preferences of these players might be in two different ways that we are going to discuss in this course. It can be ordinal, that is, this theta I is just defining the ordering over these outcomes. It does not have any real value associated with it. Maybe in an election, a particular individual, a particular voter likes candidate A over B over C. So that will be considered as an ordinal preference of that individual. On the other hand, you can think of there exists some real number. So whenever you pick a particular action or pick a particular outcome, so from this set X, and depending on what your type is, you get a particular real number. And this mapping of this outcome and your type set to this set of real numbers is denoted by the utility of this player. And this is true for what we call the private value model. That is, you only care about your own type. But if you also care about others' type, so this is the capital theta, that is the Cartesian product of all these capital theta i's. So utility of agent I does not only depend on his own type, it also depends on the types of others. In that context, we call this an interdependent valuation model. So these two kind of utilities, you can actually define utilities in more general way, but we'll be mostly considering with this private value model here. So here you can think of it also induces some kind of a preferences. So a particular outcome in this set X. So suppose agent I has a type of theta I. Now if the utility of A of this player is larger than the utility of the same player at a different outcome, which is B at the same type, then you can imagine that player I prefers A over B. So that is also another way of manifesting the preferences over the outcomes. So let us give an example of both these cases. So the voting is the example of ordinal preferences. So X in this case is the set of candidates who are contesting in this election, and theta I is essentially a ranking over these candidates. So theta I you can think of as I wrote here, A over B over C. So in this order, this is the decreasing order of preference for this particular player. That's you can think of as the type of player I. And if you are thinking about cardinal preferences, you can think of a single object allocation. So suppose there exists only one object that can be given out, maybe a painting, and the outcome is a tuple of two vectors. So the first vector is A, which is denoted by this. You have A1 to AN. Each of these numbers, so it's a vector of n elements. Each of these numbers can be either 0 or 1, and at most one of these can be equal to 1. So this inequality is saying that the object might be unallocated as well. So therefore all these AIs could be 0 also. So what does it mean that so let's say AJ here is actually equal to 1, that means that the jth agent wins that object or being allocated that object, and everybody else are not allocated that object. And the other element of this tuple in the outcome is the payment. So payment is again a vector for each of these players. So pi is the payment that has been charged to player I. So not only they are allocated that painting, they are also asked to pay a certain amount of money, and that is being denoted by this pi. Now this theta I is you can think of, so this is the private information for every agent. This you can think of as the value of agent I for that object. So if agent I gets this object, he has a satisfaction or happiness of theta I. Now it's very easy or quite intuitive to think about the utility of this player I in this case. So suppose we have a particular outcome x, and x, as you know, so it will give you both the a vector and also the payment vector. Okay, and depending on those allocations, I can just multiply the ai component of it with theta I. So if agent I wins that object, then only he gets this this particular valuation, and if he is asked to pay pi, then so that is the amount of money that he will have to shell out, therefore that is going to get subtracted. So this difference is the net utility or payoff for player I. So that also gives you a kind of a preferences over the outcome. So of course you would like to, so if you are a rational agent, then when you are not allocated this object, you should like to have this payment to be equal to 0. If you are allocated, then your payment should not be larger than the valuation. Otherwise, you will not purchase this object. So that's the objective. But this is one example of a cardinal preference. The previous one was a ordinal preference. Now so this definition, so far we have captured the agent side or the player side. Now in the mechanism design part, the designer also has an objective. And how should we succinctly represent that objective? We represent that using what is known as a social choice function. So socially you would like to have this function to be implemented. So what does that mean? So this is a function which maps each of these type sets. So each of this individual has a particular type which comes from this set. Theta player 1's types comes from capital theta 1. Similarly, player n's type comes from capital theta n. This function maps those the type vector into an outcome which is in the set capital X. So what are the examples? I mean, this is a little abstract definition. Let's understand what it means. So let's say in voting, if you have a candidate who beats everyone else in pairwise contests, so you are counting the ballots of all the voters, and you figure out that and imagine that these voters are giving the complete preference ordering over all the candidates. Then you count how many times this a particular candidate beats everybody else. So if there exists a candidate who beats everyone else in pairwise contest, then that candidate must be chosen as winner. So that could be one constraint on this social choice function. That is our desirable outcome. Or alternatively, you can think of that if there exists some preferences, so for all the players, A is on the top. It doesn't matter what is the alternatives or candidates, A is on the top. So everybody is unanimously liking A. Then that outcome, candidate should be chosen as the outcome of f of theta. So that is another desirable property which can be captured by this social choice function. So in the context of public projects, so let's say theta i's are mapping these outcomes. So whether you are building a bridge, that gives a particular agent a specific value, where if you are building a park, that gives a different valuation. So depending on that, so if this is the type theta I, which is a mapping from X to R, then f theta could be to maximize the sum of the valuations of all these players. You pick an alternative that maximizes the sum of all the valuations of all the agents. So that is another example of a social choice function. We'll discuss all these different kinds of social choice functions in detail. Now the objective of mechanism design is to make sure that no matter whichever kind of social choice function you pick, that social choice function should emerge as an outcome of an equilibrium of the induced game. Now you can see that there is a game going on. Once you have fixed the social choice function, the players can potentially change or report their types in different ways to get whatever they prefer more. And there could be a conflict of interest. And how can we actually ensure that the true f theta that we wanted to implement comes out as an outcome of an equilibrium? So in order to do that, to create a game where if theta emerges as an outcome of an equilibrium, we need mechanisms. So what is a mechanism? In a more general term, we can define an indirect mechanism. So we'll come back to this point, what is the difference between an indirect and a direct, in a few minutes. So an indirect mechanism is something where every player has been endowed with a message space. So this M1 to Mn are the message space for the player I, and G is something like an aggregation rule. So once every agent has picked their messages, so you can think of that the players have been given this message space, and depending on their types they can pick any message from this message space. And now this aggregation rule comes in, it picks everyone's messages and pops out one outcome. Right? That is one indirect mechanism. Now what is a direct mechanism? You could have actually asked the players to reveal their type itself. So this message spaces could have been the type set theta, capital theta I itself. And this aggregation rule is nothing but the social choice function itself. So that is a more direct way of asking the agents about their types and what the mechanism design is trying to do, that is given by this social choice function, that we will call the direct mechanism. So indirect mechanism can be shown in the form of a schematic. So you have this decision rule or the aggregation rule at the center, and each of these M1s which are coming from this message space capital M1, each of these agents, player 1 to player n, they are choosing one of these messages that is coming to this decision maker, who will implement this function G, and that will give out some outcome which will be in the set of all outcomes, right? Now this you can think of, this is a kind of a little unusual way of defining a mechanism. Instead of asking their types directly and implementing the social choice function, we are going in a little roundabout way. There are two reasons for it. So one reason is that sometimes it may not be possible to find a kind of a relationship between this direct mechanism and indirect mechanism. So therefore we'll have to go via the indirect mechanism. The other reason is that the implementation might not be that easy for direct mechanisms. Rather, endowing them with some message spaces which are much more easier for the players to handle. That could be one way of implementing this. But we'll see that this kind of indirect mechanism are not very commonplace, and that is due to a result that we'll come to very soon. We have already discussed about weak dominance and strict dominance in our discussions in game theory. Now, in the context of this indirect mechanisms, we can define this weak dominance. So suppose we consider an indirect mechanism given by that, and we call a message Mi is weakly dominant for player I at a particular type theta I if the following happens. If you look at the utility of player I, when player I is choosing this message Mi, and other players are choosing some arbitrary message which is given by M minus I tilde, and this utility is evaluated at the type when theta i's player i's type is theta I, and this utility should be at least as much as the utility when this agent is moving to some other message Mi prime. If this holds for all M minus I tilde, so note that this is the requirement for dominant weak dominance. It should hold for all M minus I tildes, and it should also hold for all Mi prime. So This inequality is actually saying that this strategy, the message mi is weakly dominating all other messages in that message space. So that's the definition of weak dominance for messages. You can actually cast this this definition in the context of ordinal preferences. So all the definitions that we are going to give in this module and in the subsequent modules are going to assume cardinal preferences. So we use these utilities and inequalities because these are real numbers. But you can also replace this with ordinal. For instance, the same inequality, this inequality could have been written in the context of ordinal preferences in the following way. So theta 1 in that case is a preference order. So we can say that A theta I B, that means that you prefer A over B. So this is more preferred than B. So, so using this notation here, what we are saying is that if you pick this mi and the other players are picking m minus I tilde, then this is the outcome that you are going to get. Because this is the mechanism, G is going to take those messages and going to pop out the outcome. That outcome will be more preferred than the outcome if you have moved to mi prime. And this should also hold for all mi prime and also for all m minus I tilde. So this is the restatement of the same weak dominance in the context of ordinal preferences. Now we will say that a social choice function f is implemented in dominant strategies by this indirect mechanism m1 comma to mn comma g if there exists some message mapping. So these are, you can think of as strategies. So you have a particular type. So your type is coming from this set theta I, and you apply a function si on that to get something which is belonging to this message space mi, right? So that is what is meant by this function. And then what is the property of that message mapping si? It is a dominant strategy for agent I at theta I, and this dominant strategy is already defined in the previous definition. So this should hold for all small theta I in capital theta I and for all players in n. So that is one condition, and the other condition is in that equilibrium. So you can think of this si comma s minus I, this strategy profile is a dominant strategy equilibrium for all these players. And what should happen in that equilibrium? If you apply G on top of that, so note that these are all elements in this M1 to Mn, the message spaces. The outcome should be the same as the outcome that the social planner wanted. This is the f theta that we wanted to implement. So by going via this indirect mechanism M1 to Mn comma G, you are implementing the same outcome f of theta in a dominant strategy. So then we'll call this social choice function f is implemented in dominant strategies via this this indirect mechanism which is given here. So there is another nomenclature available for this. We call that this is an indirect implementation, and that this social choice function is dominant strategy implementable, or DSI in short, by this mechanism, by this indirect mechanism. In the context of direct mechanisms, we will use a different terminology, and this is known as the dominant strategy incentive compatibility. Now there is no other mechanism because we are implementing it directly. All the message spaces have become the type sets itself, and the decision rule is the social choice function itself. So this direct mechanism, we'll call this as dominant strategy incentive compatible. If the following thing happens, it's again the very same thing. Player I is reporting his type truthfully, and other players are reporting whatever they want to report. And for player I, evaluated at that particular type, theta I, the utility is at least as much as the utility when he is misreporting his type to theta I prime. This should hold for all theta I prime, theta minus I tilde, and for all players. If that happens, then we'll call this direct mechanism dominant strategy incentive compatible. Now the trouble here is that if we want to find out that a social choice function f is dominant strategy implementable by some other indirect mechanism, we need to search over all possible indirect mechanisms, and there is a very large set. Luckily, we have a result which we'll see in the next module that reduces this search space. So we don't really need to search over all indirect mechanisms, rather we can only depend on direct mechanisms.